In this video, we're going to be talking about exponential growth and decay model. Now, we've got two things over here. We've got the differential equation, or if you did the antiderivative of this thing, you get y equals c e to the kt. C is our initial value, what we're starting with, and k is our proportionality constant. It's kind of like about how quickly this thing is growing exponentially or decaying exponentially. So let's see where some of that stuff comes from. We've got the differential equation, just like we had before. We know what k is, and we know what our initial condition is. So let's see where those things come from. So if we plug in k into our thing, we get dy over dt equals negative 0.5 t. No, y. Excuse me. Oops, because see, there's a y there. What we want to do after that point is we want to figure out what the initial condition is, but to do that, we have to anti-differentiate. So we don't like that the dt is over with the dy, and we also want to make sure that y is over with our dy. We want to separate our variables. So we get 1 over y dy. Why do I keep running a t there? Dy equals negative 0.5. Don't want to write the negative dt. And then we integrate both sides. So integrate. So the anti-differentiation of, if we integrate 1 over y, we get the ln of y equals, and on the other side, we get negative 0.5 t plus some c value. All right. Next, we want to try to solve that thing for y. So we're just going to raise both sides to an e. Boop, boop. Come on. Come on. I know you can do it. There you go. The e and the ln are able to cancel each other out, so we're left with just a y. On the other side, since we've got those two exponents being added together, because you want to imagine that, hey, both of those things are part of that exponent, that means it is e to the negative 0.5 t multiplied by an e to the c. And if we've got an e to the c, that's still just a constant. So this e to the c that we've got right there, we can kind of get rid of that thing. And we're left with a c e to the negative 0.5 t equals y. And you can see how that matches up with what we had originally. Let me just steal that from over here. Boop, boop, burp, wop, bop. So our y equals c e to the kt. So k is still our proportionality constant. No, what do we call it? Yeah, I said it right. Proportionality constant. But we were giving an initial condition that y of 0 equals 200. So if we put in 200, let's see what we get. So that would be 200. Hey, can I have a pen, please? So 200 equals CE to the negative 0.5. And then our exponent of 0. Well, negative 0.5 to the 0 times 0 is 0. So we get e to the 0, which is 1. So we get c equals 200. So we could just plug that right back in for our c value right here, and we're able to get our exponential model for this problem. 300, 200 e to the negative 0.5 t. That satisfies our initial condition. Now we could just jump right to this thing based on the information that we were given, but I wanted to show where this formula comes from. So in this one, we've got that dy over dt equals k thing, but we know that means the same thing as this. So rather than putting our values into this equation and anti-differentiating, we could do all that stuff, or we could just save ourselves some trouble and we can plug it into this thing. We do have a problem though. They're not being very clear about what our c and our k is, but we know c is our initial value. And take a look right here. This is telling us what our c value is right here. Could I have a pen, please? Oh my gosh. So this is saying that our initial value where we're starting is 60. Now, this is not quite k. This is going to help us find k. So let's put in the information that we know so far. So we know that y equals 60 e to the k t. We're not going to get anything for t. T is going to stay a variable just like the y is. But we can plug in our information that we've got from that other point in order to solve for our k value. So we could say, all right, well, 30 equals 60 e to the k. We don't know what that is. I was about to like put in a value there, but I'm like, what is k? Oh, we're trying to find it. And then the time that we're given is 10. So we just need to solve this equation for k. All right. Let's get rid of that 60. So we get 1/2 equals e to the 10k. Then I want to get that exponent out of there. So we want to do the ln on both sides. So we do the ln of 1/2 equals 10k, because if I do the ln of this side, it'll just get rid of our e. The ln of e is going to be 1. So now we just divide by 10, and then we've got our k. So we get the ln of 1/2 over 10 equals k. We can do some stuff with it to try to clean it up a little bit. I know that this thing K is going to be heading right there, and then there's going to be an E right there. So if I could somehow get everything inside of this ln, and then it's with that E, oh, that's going to make my final answer look pretty nice. Remember, we're not really in the simplification game, but it's always nice to know some of these tricks so that if it shows up as a multiple choice option, we know what to do. So that divide by 10. So divide by 10 is a 0.1. That's a tenth. And then we've got the ln of 1/2. Well, that's a 2 to a -1 exponent. And if you're multiplying in front of a logarithm, you can bring that in as an exponent of the inside. So this is still k, equals k. So this is the ln of 2 to the -1 to the 0.1. Well, that's just the ln of 2, because then we can multiply these two exponents together, to the -0.1. And we're doing that because we're about to put it into this k spot. And by doing it this way, then that ln and that e are going to kind of mesh together pretty nicely. So I think we're prepped. So now we're going to bring that into our y equation. So we got y equals 60 e, and then we're going to bring in our k value, which we just found, which is ln of 2 to the -0.1. And that's also being multiplied by t. And I put it in front because then you can kind of notice, hey, it's doing that same thing that 0.1 is. So, yeah, let's bring that in there too. More the merrier. So that's y equals 60 e to the ln of 2 to the -0.1 t. Oh, okay. Now these two things are able to undo each other. And so we are just left with y equals 60 times 2 to the -0.1 t. So we could have just left it with this big old mess. That's fine. We could even put like this blue mess right here in this k spot. But, sometimes it's nice to think about that simplification because you never know if that's going to be one of our multiple choice options. So concludes our exponential growth and decay model. To keep in mind, you might get that dy over dx equals ky, but we can always just quickly convert that without doing any of the integration into y equals ce to the kt. C being our initial value and k being our proportionality constant. Thanks for watching. Bye-bye.